Hi there, my name is Aubrey, and this is my discussion video over review. So the topic that I chose was review over general chemistry, talking about Lewis structures, resonance, bonding, hybridization, and formal charge. So the first topic is Lewis structures. A Lewis structure is a simplified representation of the valence electron or valence shell electrons in a molecule. So it helps visualize how the electrons around the atoms in the molecule are arranged. So when looking and drawing a Lewis structure, it's important to remember that the dots are electrons, so the dots surrounding a atom are electrons, and the bond, so the dashed line, is shared electrons between two atoms in a molecule, which we know. To draw a Lewis structure, it's best to first find the valence electrons in the molecule, which is the total group number of all the atoms involved plus the charge. So the example that I'm going to be talking about today is nitrate, so NO3 minus. So N's group number is 5. Oxygen is group's number is 6, but since we have 3 oxygens in nitrate, it'll be 6 times 3, which is 18. And then the charge adds a 1. So the total group number for nitrate is 24. So next, we draw a skeletal structure for the molecules, which connects all the atoms using only single bonds. So that is what this one looks like. I drew some pictures. So important thing to remember is that the central atom will be the one in the middle of the structure. This is the one that can form the greatest number of bonds and or expand its octet. So in this case, nitrogen. When you add the lone pair of electrons, which is finishing the atom's octet, it's important to remember, so the bonds between the oxygens and the nitrogens are already counted, but we now add the remaining electrons. So 2 electrons form a bond, so I drew that one right here. So drawing all the different lone pairs, and then these dashed lines are already shared electrons between the N and the O's, or nitrogen and the oxygens. So important thing also, completing octets, distribute the remaining electrons to satisfy the octets of the atoms. So in this case, nitrogen's octet is not fully filled. So in that case, we would take one of these lone pairs of electrons and make a double bond with nitrogen. That will give nitrogen more electrons bonded to it, and complete its octet. So yeah, in this case, the nitrogen is short 2 electrons, so we can use a lone pair from the left oxygen atom to form a double bond and complete the octet of the N atom. So check the structure, make sure the total number of valence electrons is present and that each atom has a full octet. Next, I'm going to be talking about formal charges, and we'll still talk about the nitrate example. So before finishing the Lewis structure, formal charges on each atom must be added. A formal charge is a charge assigned to an atom in a molecule, assuming that electrons in all chemical bonds are shared equally between atoms, regardless of relative electronegativity. The formal charge of any atom in a molecule can be calculated by the following equation. It's the group number of an atom minus half the number of bonding electrons minus the number of lone pair electrons. So this is a good equation just to be able to just calculate it, or from just experience and us all being in chemistry for a while. Some of it's just kind of easy, like we know carbon has 4 bonds, nitrogen is 3 bonds and 1 lone pair. oxygen, 2 bonds, 2 lone pairs. We kind of know that just from, practicing chemistry a lot. But if you didn't, that equation is how you can find the formal charge. So in terms of nitrate, this is how the charges would look on each atom, and I drew that down here. So the group number would be the group number right here is 6 for oxygen, -1 just for one bond bonded to nitrogen, and then -6 for the number of lone pair electrons around this oxygen, which gives it a -1. With this one, this oxygen is double bonded to nitrogen because we took one of the bonds off and shared it. So we have 6 minus 2 of these bonds minus 4, because there's only 4 lone pairs, or 4 electrons, 2 lone pairs. So that's neutral, and then this last one, N, is a +1 charge, and I have that down here. It's probably going to be backwards for you guys, so I just realized that. And then it's important to remember with formal charges, the fewest number of formal charges possible. So example, like 0, like a neutral charge, for as many atoms in a structure as possible is the goal. We want to try to have that. And then formal charges should match the electronegativity of an atom. So negative charges should be on the more electronegative atoms, and then positive charges should be on the least electronegative atoms. And then the next topic I will be talking about is resonance. So this is basically describing that there is sometimes more than one correct Lewis structure that can be drawn for a molecule. So that's called resonance structures. So for example, with nitrate, or NO3-, there is 3 correct ways to draw the Lewis structure. So when we took a lone pair of electrons from the left oxygen to make a double bond with nitrogen, that was one way to do it, but we didn't have to just take it from this left oxygen. We could have taken it from the oxygen down below here, or down below here. So there's 3 different oxygens we could have taken a lone pair of electrons to and made a double bond with nitrogen. And I drew these on the back just to show. So these are all correct ways of drawing. With drawing the resonance structures. And then it's also important to remember that resonance structures only change when it comes to electron pairs, not the placement of atoms. All right, so the next topic will be over bonding. So a few things just to remember. The shorter a bond, the stronger it is, and the longer the bond, the weaker it is. So longer bonds are a result of larger orbitals, which presume a smaller electron density and a poor % overlap with the s orbital of the hydrogen. This is what happens when we move down the periodic table. Therefore, the Hi to HF bonds become weaker as they get longer. So for example, bond strength increases from Hi to HF. So HF is the strongest bond while Hi is the weakest. And then the bond strength is inversely correlated to bond length. And there's different types of bond length and strength according to like the structure. So like alkanes, like a CC bond in alkanes must be the longest as it is the weakest, and the CC bond in alkenes is the shortest and it appears to be the strongest. So in this case, like the bond length decreases going from sp3 to sp hybridization. So that kind of goes into this next topic is hybridization. This topic for me has probably been one of the most difficult for me to kind of grasp just in my chemistry journey. I slowly understand it. It's a lot easier, I feel like, when I have like a chart or, all the different hybridization, geometry kind of shapes, I guess, of the orbitals. But this one, I feel like, is a little bit harder to explain, so hopefully you guys are able to follow me. But hybridization in organic chemistry is basically the process of combining atomic orbitals to create new hybrid orbitals with distinct shapes and energy levels. So this idea is essential for understanding the geometry and bonding characteristics of molecules. So first thing with hybridization is you are counting the number of electron domains, so the bonds and the lone pairs, around the central atom. So in nitrate's example would be nitrogen, that's the central atom. And then based on the number of electron domains, so bonds or lone pairs, assign the appropriate hybridization. So if there's 2 electron domains, it's an sp. If there's 3 electron domains, it's an sp2. If there's 4 electron domains, it's an sp3. So I'm going to explain what that means: sp3, sp2, and then sp. There's lots of different things underneath each category, but sp3 hybridization is a tetrahedral geometry shape. This occurs when 1 s orbital and 3 p orbitals mix to form 4 sp3 hybrid orbitals. So example, like each hybrid orbital has like a 25% s character and a 75% p character. Each one of these has a different bond angle, so this one is 109.5, and then an example of this would be alkanes. sp2 hybridization is trigonal planar geometry. This occurs when 1 s orbital and 2 p orbitals mix to form 3 sp2 hybrid orbitals. This is a bond angle of 120. An example of this would be alkenes. ALKENES. And then sp hybridization is linear geometry. This is what occurs when 1 s orbital and 1 p orbital mix to form 2 sp hybrid orbitals. So each hybrid orbital has like a 50% s character and a 50% p character. Bond angle in this one is 180. An example of this is alkynes or alkene, the ALKYNES example. And then some important factors that hybridization offers. It determines molecular geometry. So understanding an atom's hybridization helps predict the 3-dimensional arrangement of its bonds and lone pairs. And then it ultimately helps enhance bond strength. So hybridization improves orbital overlap, resulting in stronger and more stable covalent bonds. So that was all the review for me, and sorry this was such a long video, but hopefully you guys were reviewed in the Gen Chem important aspects. So thanks.